Hello, Physics 1 students. In this video, I want to describe how to go about calculating moments of inertia for different shapes in different situations, and then how to combine after you know a table, after we kind of have a table of basic shapes, how can you combine them to build up more complicated scenarios? So along the way, we will calculate directly the moment of inertia for a rigid rod. We will discuss something called the radius of gyration, and then we will describe something called the parallel axis theorem, which is a way to use knowledge about rotations of one axis to figure out the moment of inertia for another axis. That's quite a bit, so let's get started. Our first task is to go through maybe the simplest calculation of a moment of inertia, other than a point mass. So we already know for a point mass, the moment of inertia about an axis of rotation for a point mass is simply the mass times the radius perpendicular to the axis of rotation squared. That's easy. Usually people just write this as mr squared. If you look it up, that's what you'll see. But I like to write the subscript perpendicular just to remind myself of what I'm actually meaning by this. What I want to do, the next simplest situation is if we have an axis of rotation. I'm going to put it right down, put it in green here. Axis of rotation. And then I'm going to imagine that I have a rigid rod. And we'll go ahead and let this have a length L. And this rod will be allowed to rotate. Put that in blue there. Rotate about the axis of rotation. So the rod is going to rotate. It has a total length L. And we'll go ahead and say that it has a mass M. And we're going to assume that the mass is evenly spread out. Variable densities are just a complication. So we can assume that there's a linear mass density, lambda, which is simply the total mass divided by the total length. We'll assume it's just a constant for us. The nice thing about that is it's going to allow us to relate the mass of a segment here, a little arc length segment, to the size of that segment. In particular, well, let's go to the next page and we'll kind of zoom in. So if I have a length L and I identify a little chunk of it, that little chunk has length dx, and it's going to have a mass dm, and the relationship between them is formed using the density. Specifically, I know that the mass of that little segment is the density of the mass density times the length of that little segment. Okay, so that's a handy little formula to remember. All right, our formula for the moment of inertia of this object is that the moment of inertia is the integral, I should mark my axis of rotation before I forget. It's through the center. Okay. The formula for the moment of inertia is the integral dm of r perpendicular squared for each little chunk. So I marked out one, but in particular here, then, for a generic element, r perpendicular is nothing other than x, the displacement along the x-axis, because I've aligned the shape with the x-axis. So I can turn this integral formula into the integral. I substitute in for dm, it's going to be lambda times dx, and then r perpendicular is going to be nothing other than x squared. And then I just rearrange this. Oh, and then I integrate. Well, okay, so the total length is L, and our perpendicular, or x, ranges from minus L over 2 to L over 2. So I'm going to kind of rewrite this here. Lambda, I'm going to pull it out. It's a constant. It's going to be m over L. That's lambda. And then I have the integral of x squared dx from minus L over 2 to L over 2. That is my formula for the moment of inertia. So I have to do this integral, and I get this equals m over L. This integral gives me x cubed over 3. And I have to evaluate it between negative L over 2 to L over 2. And when you do that, this gives me m. I end up with a 1/3. Because it's a cubed power, the minus sign kind of comes in, and they double, both of the two contributions to this double up. And I have a factor of 2 to the 3rd in the denominator, and all that comes together to give me, let me actually rewrite this. It comes together to form 1/12 the mass times L squared. Now you should check this. It's not hard, just simple calculus. Okay, so that is the moment of inertia for this rod rotating about its center. And if you go back and you check the video where I showed you the list of moments of inertia, or if you check your textbook or you check Wikipedia, you'll find this is a standard value that is given. I want to comment, when they say L, they mean the total length of the rod, not, sometimes people, the distance from the axis of rotation to a point on the edge is actually L over 2. So the formula is expressed in terms of the total length L. All right, let's do another example. Let's take the same rod, but now, rather than rotating it about the center of the rod, let's rotate it about the end of the rod. Okay, so it has the same length L, same mass, and lambda then is still the same, m over L. So nothing about that has changed. It's really physically the same rod. We're just changing the place where we rotate it. Let's talk about what we're expecting. We're expecting that the integral will be larger because the typical perpendicular distance from the axis of rotation is larger when you rotate it this way. So we're expecting a larger number. That's okay. So it's it always helps me to kind of mark out just a typical chunk or a random, or just a segment out here. And that segment has a perpendicular distance, which is just given by x. But this time, x will range from 0 out to L, whereas last time it ranged from minus L over 2 to positive L over 2. So I can just go through my formula. The moment of inertia equals the integral of dm times r perpendicular squared. And then I substitute everything I know. I write that as lambda times dx for the mass differential. And our perpendicular is just x again, squared. And I integrate from 0 to L. Pulling out all the constants, this equals lambda, which is m over L, times the integral from 0 to L of x squared dx. Plug this in. This gives me m over L, and I get a 1/3 times x cubed evaluated between 0 and L. And when you evaluate that, you find I for a rod about the end is 1/3 ml squared. So this time we get a 1/3 fraction out front, whereas in the previous example, we had a 1/12. 1/3 is bigger than a 12th. So we find that the moment of inertia is larger when you compute it about the end of a rod than it was when you computed it about the center of the rod. And that makes sense, because if you think about moments of inertia as just, or as integrals as just sums, we find that when you rotate it about the center of the rod, the typical term in the sum, the typical radius that you get, is smaller than it is when you rotate the rod about the end of it. So here, the typical radius is, I don't know, something like half the length, whereas before it was something like a quarter of the length. So the intuition matches, and we can come up with a quantity to kind of characterize the spread. So moments of inertia, integral dm of r perpendicular squared, they are sensitive. I don't mean they're in touch with their emotions. I mean they are sensitive. They know about the spread of matter about an axis. And the more spread out the matter is, the larger the moment of inertia will be. We can actually do some unit analysis to motivate a definition of a quantity, which will kind of quantify this concept. The units of moment of inertia are mass times length squared. So we can define a quantity, k. It equals the square root of I over m. So the units of k are meters, or length. In the metric system, it's meters. And k is called the radius of gyration. So it sets, or it measures the size of the typical distance of a typical piece of mass away from the axis of rotation. It just gives you a measure of the spread of mass. Excuse me. If we were treating the pieces of mass statistically, then k is kind of like knowing the standard deviation, or it's actually better, more accurately, it'd be like the root mean squared distance away from the axis of rotation. That's probably a better way to define it. Anyway, if those words don't mean anything to you, don't worry about it. I don't want to go into it. It just, if you had statistics, maybe that helps. If not, just think of k as measuring the typical distance a chunk of mass is away from the axis of rotation, the radius of gyration. We can apply it here to find the radius of gyration for a rod about the center. That would simply be the square root of 1/12, the mass times the length squared divided by the mass, equals the square root of 1/12 times the length of it. And let's think about that. What number times itself gives you 12? Well, I know 3 squared is 9, and 4 squared is 16, so can't be too far off to say this is about 1 over 3.5-ish times L. I'm going to use an actual calculator rather than just kind of winging it here. So I'm going to say 1 divided by the square root of 12. Okay, there you go. Let's just, what is that? Oh, not bad. All right, the actual answer was, or the better estimate was 3.464, but anyway, when I put it all into decimal form, this comes out to be about 0.28 times L. And if you remember, just eyeballing it, I kind of estimated that, oh, when you have an axis of rotation in the middle, a typical chunk of this, if the whole arm here was L over 2, I estimated it was like L over 4, when in reality it was apparently 0.28 times L instead of 0.25 times L. K for a rod rotated about the end would be given by the square root of 1/3 ml squared divided by m. So that's going to be like 1 over 3, take the square root, and times L, and typing in numbers gives me 0.58 times L. And so we put the axis of rotation on the end as length L, and remember my estimate was it was something like half of L would be a typical location of a chunk of mass relative to that, and the radius of gyration calculates to be 0.58, so a little bit bigger than what my estimate was, but that's okay, it's just an eyeball guess. All right, so this radius of gyration captures the idea of whether the mass is kind of compact and close to the axis of rotation or spread out. And it gives you just a quantifiable way to characterize that spread. Okay. So now, having seen how to calculate moments of inertia for rods, the 1D examples, and that's really the extent of what you would have to do using calculus in this class. For the other shapes, other simple shapes, we can just look them up. Let's talk about how you combine moments of inertia for different objects to build up more complicated shapes. So, so what I'm imagining is, let's say we have an axis of rotation. Oh, let me put a title here. This is combining moments of inertia with a common axis. So that's important here. All right, so the picture I have in mind is that I have an axis of rotation here, and then I have, I have some objects here. And for some reason, they are rigidly rotating. I don't know why, but that's not my problem. It's the problem of whoever made the problem up, to justify that assumption. So let's assume we know, let's label these as 1, 2, and 3. Assume we know the moment of inertia of I1 about this axis, I2 about the same axis, and I3 about the same axis. So we know those numbers, and we want to know if we rigidly rotate all of them together, we synchronize their rotation so they move rigidly, what is the total moment of inertia? Fortunately for us, when you have moments of inertia of different objects about their same, or about the same axis of rotation, that's simply the sum. So it's going to be I1 plus I2 plus I3. If you think about it, that's not a surprise. We really used that principle when we wrote down when we went from the moment of inertia of a point mass to the moment of inertia of the total shape. If the moments of inertia are known about a common axis, you can just add them to find the total moment of inertia. Let's do an example. Let's imagine we had, well, okay, so let's imagine we have barbells. Okay, and let's imagine that we put the mass on there and they're not balanced even. So, and being so strong, I'm going to try to hold this right about the center of the rod. So my axis of rotation I'll take to be around the center. That's the place where I'm going to try to hold it with my finger. I know Billy's pretty impressed right now. And just for some numbers here, let's go ahead and let this be, have a mass of, oh, I don't know, 20 kilograms. And we'll let this have a mass of 10 kilograms. And we'll let the rod have a mass of, oh, let's say it's 5 kilograms. Okay, and I would like to know, so obviously I'm going to have trouble. There's an unbalanced load. It's going to want to rotate about my finger, which is on this axis. So as I'm thinking about this, I'm going to want to know what is the moment of inertia of this shape about my finger. No, Dylan, I don't mean that finger. I mean my pointer finger. Clean thoughts here. Stay with me. All right. So to do that, well, I'm going to treat the spheres. I know I drew them kind of big, but I'm going to pretend that those are point masses for our purposes. You don't have to, but it just sort of complicates our life a little bit. So I'm going to pretend I'm going to treat these as point masses. Just so you know, in sapling, when they start talking about kids on a merry-go-round, you're supposed to treat the kids as if they are points. You're not supposed to worry about the actual shape of the child. Just treat them as points on the merry-go-round. Okay, so, well, all right, that's fine. The moment I know the effective radius of each of these point masses, that's just going to be L over 2. So I can think about the moment of inertia as the sum of 3 contributions. It'd be I of the 10 kilogram mass plus I of the rod or the bar plus I of the 20 kilogram mass. And I just have to apply my formulas carefully for each one. So I'll do that on the next page. I for the 10 kilogram mass, that's like a point mass, so that's just going to be mr squared, which when I plug in numbers, that's going to be 10 kilograms. Oh, hold on here. I need to give you a length. Sorry. Assume, put that in red since I forgot it earlier. L is, let's just take it to be 1 meter. Okay. So we'll assume L is 1 meter. If L is 1 meter, then the radius experienced by the 10 kilogram mass is going to be half of a meter, 0.5 meters squared. So this is going to be 0.25 times 10 is going to be 2.5 kilogram meters squared. The moment of inertia of the bar, well, that's a bar rotated about its center. That's going to be 1/12 the mass times the length squared, the total length. So that's going to be 1/12 times the mass of the bar, which I said was 5 kilograms, times the length squared, which I said was 1 meter squared. So that's half of 5. It's, again, 2.5 2.5 kilogram meters squared. Check if I got the numbers right. Half, oh dear, I didn't get it right. I forgot to write the 1. It's not a half, it's supposed to be a 12. So this is wrong because I needed to put in that it's 12, not a half. So hold on a second here. This should be 12. All right, so I'm going to erase that. Try again. Do it again, but better. Okay, it's 1/12 ml squared. So I have 1/12 of 5. I'll just cheat and use my calculator. There you go. That makes more sense that it's smaller than the 10 kilogram mass result. So that's going to be 0.417 kilogram meters squared. And then I can write down the moment of inertia of the 20 kilogram mass. So that's just going to be like a point mass. So the mass is, so that's going to be m r squared. The mass is 20 kilograms. The radius, well, the radius is half of L, half a meter squared. Hold on one second. Did I follow that up? No, that was right. Sorry. So that's going to be 0.25 times 20. That's going to be 5 kilogram meters squared. So I total is the sum of all of those. So that's going to be 2.5 plus 0.417 plus 5 kilogram meter squared. And assuming I've done all that right, I get 7.5 plus 0.41 equals 7.917 kilogram meter squared. Amazing. Works out just right. And if you want, we could calculate a radius of gyration for the total object. And that would simply be the square root of I total over m total. And that's going to be that divided by, see, the total mass is going to be 20 plus 10 plus 5. So that's going to be 35. And then you take the square root. And I find that the radius of gyration is 0.476 meters. So let's look at that shape. Does that make sense? What's the typical distance? Not the average position, because when you just take the average position, you get pluses and minuses. We're looking at the average of distance, really. That's how you should think of it. So you don't worry about the minus signs. So, okay, over here, I'd say the average distance, well, it's going to be predominantly the ball on the end. So it's somewhere closer to L over 2, so about 0.5, but maybe a little bit inwards because of the rod. And over here, it's even more so. So it's basically concentrated on the outer edge. So it should be pretty close to L over 2, which would be 50 centimeters. The actual number we get is 42 centimeters, or sorry, 47, 48 centimeters. So it's pretty close to concentrated on the edge. And if you think about lifting weights, not that I do that a lot, might surprise you. I have this physique naturally. But if you think about lifting weights, the sort of the rod makes a pretty minimal kind of effect. It's really all about what's happening on the ends of the rod that matter. As far as rotational motion. Okay, so we've talked about how to combine objects rotating about the same axis, and I think I'm going to stop there, and I'm going to have another video on something called the parallel axis theorem. I'll push that to the next video because this one's getting kind of long. All right, see you next time.